Hi, my name's Richard and I'm the founder of Mobineko. If you've never heard of us, we're a small pressing plant based here in Taiwan. If you're a musician who's ever thought about pressing vinyl, then you might actually have pressed your records with us, or at least come across us somewhere. I started Mobineko when I was 14, which is almost 30 years ago now, but pretty much every day I keep learning something new about vinyl. Before we start, I think it's important to show you hands-on how music gets cut onto a lacquer, then how that actually ends up as a bunch of records. I've seen lots of videos that show lathes or pressing plants, but there's usually not much detail about what's actually going on. I'm not going to make any assumptions about what you already know, but we'll also get quite deep into the science and theory of vinyl. If there's anything that doesn't make sense, just let me know in the comments and I'll try to make a follow-up video. If I'm training a new technician, the first thing we'll do is start at the studio, and specifically we'll go through all the general parts of the cutting lathe and what they do. So let's go there now and take a look at the lathe. So a disc cutting lathe, just like this one, is just a very precise turntable. The star of the show is the head, and this works in reverse compared with your standard deck at home. A normal turntable is actually really simple, which is what makes them so ingenious. A stylus is dragged across a microscopic groove on the record, which turns into vibrations, and those vibrations are picked up by an electromagnetic coil in the cartridge. There's some analog processing involved after that to make records sound good, but all you need to understand for now is that the sound comes from the stylus vibrating. By this point, you've probably already figured out how we get those grooves onto the disc in the first place. Instead of allowing the stylus to vibrate and generate an electrical signal for the amplifier, we send quite a powerful current through the head, which makes the cutting stylus vibrate and etch grooves onto a blank disc. There are really two main sections to a cutting lathe. First, you have the electronics that drive your cutter head and control the lathe. We'd usually call this the amp rack, since it's a bunch of amplifier components mounted in a rack. Then you have the mechanical side that rotates the platter and moves the cutter head. We call this the lathe body. One thing I find really cool about vinyl is that this lathe body is from a 1950s Neumann AM32. It still works great today, and it's kind of like working with a piece of living history. Obviously, we've refurbished it and connected it to a bunch of modern electronics, but the basic mechanical setup is the same as it was 70 odd years ago. Right here you have the amp section. We have a couple of things going on here that you won't see in a normal amplifier. The first thing you might notice is this section called feedback. This is very important on a professional cutting system because it turns this into a closed loop setup. That means the amplifier can react to what's going on in the cutting head, which gives you a much better sounding cut. We have a stereo cutting system here, so there are 4 coils in the cutter head. 2 of those are drive coils that do the actual cutting, and the other 2 are feedback coils. Those feedback coils are picking up the movement of the drive coils and feeding them back into the amplifier, where a pretty genius 1950s analog circuit is adjusting the output on the fly. The other thing that probably jumps out is the circuit breaker section. This is really important for a working studio because the amplifiers can easily push out way over an amp of power into those tiny coil wires. High frequencies especially take a lot of power to cut, so sometimes you might have an unexpected burst of white noise or a really loud cymbal hit. The circuit breakers can't catch everything, so we still have to be careful, but they do save you bacon. Sometimes on forums I see people complaining that this or that studio doesn't cut loud enough, or they didn't cut the release with enough high end, but you should probably spare some thought for those engineers. People now are making really loud, overcompressed masters at home with no control of the high end like you get from a really good old school mastering studio. As much as I would love to blast everything through the amps at max volume, one of those old cutter heads now goes for over $20,000 US. Nobody's really making new ones in any kind of volume, and I can count the techs able to repair those on one hand. Most of the studios cutting now are small operations with 1 or 2 people, and they can't afford to keep 2 or 3 spare heads on hand just in case. So if someone's thrash metal EP pops your cutter head, you could be down for months unable to take on any new work. So just keep that in mind. The next thing that's quite important is the high frequency limiter. That's connected with protecting the head too, but it also helps remove a lot of harshness if there's a lot of high frequency content in the audio. A good cutting engineer will try to set this up so the limiters are just being tickled by loud passages, and they usually only need to be set up more aggressively with something like dance music, where you have a really loud and short cut that's meant to be played in clubs. In the late 90s, every other cut was a dance music EP that had to be cut really loud to fit in with everybody else. But for better or worse, nobody really plays vinyl at clubs anymore, so unless someone specifically asks for it, I would usually ease off on the cutting level and try to avoid using the limiter as much as possible. It's important to realize that if you load up your master with absolutely tons of high frequencies, it will get limited, and depending on how far you take it, you might end up with a really crunchy sound, especially near the end of a side. That's called inner groove distortion, and I'll go into that in more detail in a later video. Further along the amp, we have the RIAA equalizer. I don't want to go into too much detail, but this is used to bias the frequencies that get cut on disc. Bass takes up a lot of space on the disc, but obviously you can't just cut all the bass out of music, so what do? Well, a long time ago, some smart people decided on a standard for certain frequency ranges to be reduced on disc, then boosted on playback, and this is called the RIAA curve. You might have heard of this before because pretty much every turntable preamp will have some kind of RIAA circuit that applies the reverse curve for playback. Some people get confused about whether they should master with this in mind or whether you need to do anything in the mastering stage to allow for it. The short answer is you should just ignore these RIAA filter circuits. They're designed to be mostly transparent at both ends, so you shouldn't worry about them. Now you have your nicely amplified signal from the amp rack, and a couple of hefty cables carry this onto the cutter head through the suspension box. The suspension box has some electronic bits and pieces, but its main job is to let the cutting stylus float and glide across the lacquer surface. Let's open up the suspension box so you can take a look inside. This knob at the back controls tension applied to the main spring, and that fights against the weight of the cutter head pushing the other way. We can adjust the depth and width of the groove by turning this knob, and we're aiming to get just the right balance to get a nice consistent width as the disc spins around. Just as an aside here, in the 80s and 90s there were three major players in the blank lacquer disc market. You had Transco in the UK, Apollo in California, and MDC in Japan. At some point Apollo bought out Transco, but there was still some healthy competition between the Americans and Japanese, so if you weren't happy with the quality from one supplier that month, you could always flip to the other for a while. Unfortunately, a few years back, the Apollo lacquer factory literally went up in smoke. Lacquer discs are made from nitrocellulose lacquer, the same stuff that nail polish is made from, and a really volatile, flammable chemical. Back to the lathe. We're talking about this spring inside the suspension box that regulates the cutting depth. Anyone who's ever worked on cars will know that suspensions usually need some kind of damper to smooth out bumps and vibrations. And our lathe has one too. This oil-filled container is called a dash pot, and we can adjust the reaction using a small knob on the piston here. Once the tension screw and dash pot are set up just right, you can happily cut a nice consistent groove even in a fairly lumpy disc. One more thing inside here is an electromagnet and a couple of switches. The electromagnet holds the head down in the cutting position, and that can be switched off by the controller so the head can be lifted at just the right moment, like that. There's also another coil in here that moves in and out depending on the current passing through it, and that's used to change the cutting depth by a small amount on the fly. We'll talk later about why that's needed. The last two mechanical parts of the lathe are the carriage and the platter. The platter is simple enough to understand, but a lot of engineering and machining went into this back in the day to get it perfectly level. This tube in the middle is used to connect a vacuum, and we have that outside the studio so it's not too noisy inside. That vacuum does two things. It sucks the disc flat onto the platter through these holes, and it also sucks up the thin bead of lacquer that gets thrown off as the stylus cuts a groove. The carriage is a bit more complicated, and this is what drives the head forward and determines how much space there is between the grooves at each revolution. We call that the cutting pitch. Back in the day, the old school engineers, who I have a huge amount of respect for, would have had to manually calculate the pitch needed for every cut, and they'd ride the speed of this carriage just by feel, so a loud passage would have enough space to cut without the grooves banging into each other. Nowadays, almost everyone's using some kind of cutting computer that calculates exactly how much space you need to fit each revolution. You can see here the lathe has been modified, so the carriage screw is now being fed from a servo motor that connects to the computer. The computer we use here is a custom design that I built on a Raspberry Pi. It's still a very manual process, but the automation in here saves a lot of time in housekeeping, and a really important feature is recall. So we can pull up an order that was cut 5 or 10 years ago and make an identical cut using all the same settings. On top of the carriage is this lever that locks the sled to the big drive screw inside here that we call the lead screw. Whenever you need to move the head manually, like at the start of a new cut, you can just flip this lever up and that decouples the screw from the sled. Just next to this lever is the helium regulator. If we look outside again next to the vacuum, you might have noticed this bottle of gas. That's helium. We sometimes use that to cool the head during a really hot cut. Personally, I don't use the helium very often. It's just there to protect the head if you have a long session where you're cutting with a lot of current and heating up those drive coils. The most valuable and important part of the whole lathe is the cutter head. In this case, it's a Neumann SX74, which is now very old, but still works just as well as it did back in the day. There's not much to see here because all the exciting stuff is packed into the case, but you can kind of see the coils are arranged in a V shape. The stylus is what actually does all the work. It's a precious stone cut into a very particular shape, usually ruby or sapphire or sometimes diamond. If you look really closely, you'll see some very thin wires coming off. Those are heater wires that keep the stylus tip warm. If you try to cut with a cold stylus, you'll hear a lot more surface noise, but also if you cut with too much heat, you can start melting the lacquer material and pushing the walls, kind of like a snowplow. We sometimes call those horns, and they can cause their own issues in plating and pressing. You get maybe 20 or 30 hours out of the stylus. We have kind of a mileage warning in our computer when the stylus is reaching the end of its life, but you can also see in the microscope when the groove's starting to look rough. Speaking of the microscope, that's another really important part of the lathe, and it's another part that we upgraded from the original 1950s design, like a lot of studios do. The microscope's used for a bunch of different things. Whenever a fresh lacquer goes onto the lathe, the first thing I'll do is make a test cut with no audio. We call that an unmodulated groove. Looking at the scope, I can confirm that the width and therefore the depth is correct. I can also make sure there's the correct amount of space between each groove. We call that the land. Usually it's safe to cut with a 10:1 ratio of cut to land. The microscope also lets you check the general quality of the groove. Whether you had the stylus heating properly, or maybe if the head or the stylus has got misaligned or just worn out. I don't want to make this too boring, so let's finish the video off with a quick cut. I already have the audio checked and set up with the EQ and processing that it needs for a good cut. Obviously we'll get into all of that in a later video. For now, we'll just go through the mechanics of cutting a normal basic LP side. I already have the audio ready to go. I have the depth set through the cutting computer at 100 microns or 1/10 of a millimeter. The platter's rotating at 33 RPM. Now I need to switch on the vacuum and stylus heater. I now need to make a test cut with a silent groove and inspect that with the microscope. A master lacquer is usually 14 inches in diameter. We can cut anything up to a 12-inch on that, and we use the extra space for test cuts. Everything's looking good. There's some movement in the groove which comes from imperfections in the lacquer blank, but this is acceptable. Each revolution is nicely separated, so there's roughly a 10:1 ratio of groove to land. Land is that space between each groove. Without that, you have no safety margin, and you might be able to hear an echo from the previous groove. I'm happy with this unmodulated silent groove, so I'm now going to play a louder section of the audio through the head, and I'm going to listen to the cut in real time from this pickup arm here. Playing back a lacquer is destructive, so we can only use this test area or an old blank to do this, and we can only do it once. Everything's sounding great, so I just need to lift the cutter head and reset the computer while I gently clean the stylus with acetone. This time I'm going to use our Mobineko cutting automation by pressing start. It's now sending a signal to the audio workstation while the carriage runs up to the 12-inch start position. The carriage has a small micro switch, and we can adjust these cams to set the recording diameter. Once that switch hits the 12-inch cam, the computer will drop the head down and start cutting a lead-in by spinning the pitch motor a lot faster. After the lead-in, another signal gets sent to the workstation which starts the audio playing. There's a lot of other stuff going on here behind the scenes, but we'll get into that later. We'll just let this get to the end of the cut, where the computer will now insert a lead out until we hit the end switch. The head lifts and we just cut a side. In the next part, I'll give you a visual insight into the groove itself, what it looks like and how it's formed. Then we can start getting into things you can do to make your master sound amazing on vinyl.